Hello everyone, this is the preview lecture for lecture 14. So in the previous lecture, lecture 13, we have discussed about the Boltzmann transport equation. So actually what we did in the previous lecture was just to consider the motion of our infinitesimal volume inside the phase space. So here the phase space is made of the real space information and velocity information or momentum information. And what we have in the previous lecture was the area or the volume inside this phase space is not changed if infinitesimal time has elapsed, but the area in this case, but volume in general is not changed. So if we have a certain number n inside our original time instance t equals 0, and if time elapsed to t equal to delta t, which is infinitesimal, then we can certainly say that there are still n particles or electrons inside this volume. So of course, this is the situation where no scattering mechanism is involved. If we have any kind of scattering event, then if scattering occurs, then for example, one electron which should be located here, however, during its motion to the position here, certainly it loses its velocity or it gains its velocity during its journey from this starting point to the final point. So it can jump into different values, different positions, and its motion can be quite much different from purely Newtonian motion. Okay, so anyway, now we understand one thing. Oh, in the semi-classical transport, Boltzmann transport equation is the governing equation and we have to solve it. However, also I told you that the dimensionality of our Boltzmann equation. So if we have, for example, three-dimensional device, then its phase space is 2 times 3, so we have a 6-dimensional problem. Of course, if we have a lower dimensionality like a 2-dimensional case, then it will be just 4-dimensional. However, as you know, even in these cases, so 4-dimensional structure is really difficult to solve. So usually, in my opinion, the maximum available dimensionality we can consider easily in these days is about 3D. So in the case of a 3D simulation, okay, we can do it within a reasonable time interval. However, problems whose dimension is higher than 3, it is very difficult to solve even with advanced computers. So you can easily imagine that the situation would be even worse in the previous times, former times, like for example 1970s or 80s and 90s, and yeah, we have 2000 and 2010, and now we are in 2020. But you know that the beginning of computational microelectronics was around here. So there was certain interest in this field. And please imagine what happens to the early researchers. So the pioneers in this field felt that actually Boltzmann transport equation that is too heavy to be solved by any means. So they had to invent certain way to an approximate solution about the Boltzmann transport equation. So that's the reason why instead of solving the Boltzmann transport equation directly, we have developed, or they have developed, many ways to get the simplified equation and solve that simplified equation. Okay, so we will now talk about the very basic ways to derive simplified equations from the Boltzmann transport equation. That is the main topic of our lecture 14. Okay, so eventually our goal is to derive so-called drift diffusion equations. So here drift diffusion equations means that two equations, they form a set of equations. The first one is continuity equation. So you know it quite well. And continuity equation, we have certain information about the time derivative of our electron density. Then this time derivative of electron density is certainly related with what? So with so-called electron current density. And now our question is, if we wanted to the dynamics of electrons, then we have to understand this quantity. Then what is the value of J sub n? So electron current density, how can I calculate it? So in principle, actually we have to also describe another dynamic equations for J sub n. How the electron current density changes when something happens inside the system. However, in so-called drift diffusion equation, usually instead of this time derivative equation, we just specify Jn as a function of what? As a function of electron density and electric field. That is our goal. And these two equations, continuity equation and another expression for the electron current density, that makes so-called drift diffusion equation for electrons. Of course, when we consider holes, we can also write down similar relation for holes. So that is just straight for the extensions. We will not explicitly consider the holes. However, please keep in mind that hole can be considered in a exactly same manner. So our goal is to derive two equations, which are basis of our drift diffusion equation. The first one is continuity equation, and the second one is the expression for the current density. Here current density means that electron current density J sub n. Yes, you know it quite well. And we will try to derive them from the Boltzmann transport equation. Here we have it, but let me just explain it once again. The time derivative of our electron distribution function is given by just Newtonian motion here, which is given by, if it has non-zero velocity, it moves. And if it has some non-zero force, then its velocity changes. So that is a simple description about these two terms. And here we have another term called scattering. And this scattering means that some unexpected behavior of our electrons, which is out of the Newtonian motion. So interaction between electron and electron, or interaction of our electrons with external environment can be merged into these scattering terms. So okay, so I will just assume that anyhow you can understand this Boltzmann transport equation, and from this Boltzmann transport equation I will try to derive first two equations, continuity equation and current density equations. And please note that here we have two different differential operator in real space and momentum space. So please keep in mind that they are different. It is because we are now working on phase space, not only inside in the real space, but also considering momentum space. So therefore we are working in phase space, and our distribution function f should be regarded as a function of real space and k space at the same time. Okay, so let's go to the first one. Here the first one is continuity equation, and we wanted to exercise the simplest one, continuity equation. So the basic strategy is quite simple. We will just integrate the Boltzmann equation. So Boltzmann equation is defined on phase space. So it has information on real space and momentum space. But our aim is actually just to kick out certain information about momentum space. So eventually we just keep the real space dependencies only. So how can you do that? So in order to make such kind of a simplification, so we just make integration of the Boltzmann equation over the momentum space. So when we take the integration, then information on the momentum space is just merged into one single scalar value, and that scalar value will be used to describe the quantity or average or behavior inside the momentum space. Okay, so now let's do it. When we just integrate the Boltzmann equation within the k space, then I will just write down in this way. So Brillouin zone. So over the entire Brillouin zone, we will make an integration. And here I have introduced a certain notation, dk vector. However, this is not actually vector. This should be regarded as just a triple integration over dkx and dky and dkg. This is just a simplified form of this triple integral. So don't be confused with this notation. And in this case, you can see that this is f and its time derivative. And here you have v times and gradient of f in real space. And here you can see 1/2 f times gradient of f in the momentum space. And here we have scattering. These are just terms in the original Boltzmann transport equation, and you can easily find certain integrals here, 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 and here, and here. So this is nothing but just the Boltzmann transport equation integrated. And here we have certain factors, 1 over cube of 2 pi, and this is just as we have discussed in our previous lecture. This one is just to count to our electrons. Okay, so if we follow this relation, then electron density inside the system can be represented by this way. So do you remember? How about this? If we just calculate Lx, Ly, Lz and 2 pi over 3 and integration of over dkx, dky dkz, then it will give us the total number of electrons. So this one just becomes the volume inside volume in the real space, and this volume is just to go to here, volume, and this one becomes just 1. And now you can easily understand this expression is nothing but just counting numbers and dividing that number by our volume. So that is the way to derive this expression. Of course, this expression does not take into account the spin. So it should be regarded as a per spin quantity, and actual electron density should be multiplied by factor 2 in order to consider the spin degeneracy. Okay, you can easily understand this one. So therefore, I will not discuss it any further. Okay, so now the main message in this slide is, okay, this is just integrated Boltzmann transport equation, integrated over the momentum space. So what will happen to this integrated form? Let's go to the term by term. So the first term can be easily converted. Okay, the first term, let's think about the first term. Here the first term is, of course, here we have round over round t, but that is just independent from this integration. And as you can see, this quantity can be easily identified as the electron density n. So the first quantity now becomes nothing but, or the first term becomes nothing but round n over round t. Okay, that is the first thing. And here we have a second term and third term. I just rewrite it, or I just copy and paste it to there. And now we have on the right hand side scattering and its integration. But as you can see that since we are working on the local scattering, so although electron at a given time, certain time t naught, let's say the scattering occurs. So now electrons can change its velocity immediately, instantaneously change its velocity. However, if we draw such kind of motion in phase space, it just means that at time equal to t naught, and if we have infinitesimally small time has passed, and now its velocity is just goes to there by scattering. Okay, that is a huge difference in the phase space. However, since we are now talking about integration over the momentum space, such an transition from one velocity to another velocity does not make any contribution to this integral. So, simply speaking, although scattering itself can be quite complicated, however, when we just integrate it over the entire momentum space, it should vanish. So here now we have just 0 here. Already we have made quite much simplification in this stage. So originally we had 4 different terms in Boltzmann transport equation, which is related time derivative and just real space motion and momentum space motion and scattering. So there are 4 different mechanisms. However, by integrating the Boltzmann equation over momentum space, the first term and the final term can be easily expressed. So now you can see that here we have second term and third term to be further simplified. Here we will introduce a certain assumption. So this assumption is quite valid in many cases. So we will assume that band structure is position independent. So what is it? It means that here we have velocity. In general, the velocity can be a function of real space and momentum space at the same time. However, we will consider a position independent band structure. So now the velocity is just a function of a real space. It is no longer related with velocity. If the momentum is given, then we have a given velocity. That is quite understandable. And if we are considering just the silicon devices, then yeah, it is really okay. Of course, if we are working with heterogeneous devices, then that will make certain difficulties. But if we are talking about silicon devices, homogeneous one, it's okay. So why do we introduce such an assumption? Why do we abandon the generality? If we introduce just position independent velocity, then here we have a real space derivative. But since this is a constant for a given position, so this real space derivative can be pulled out of our integration. So now we can say here we have real space derivatives, and yes, this is just a function shown here. Okay, so now you understand. Although this second term looks similar, but yeah. So if we have a really position dependent band structure, then we cannot pull it out here. So please note this one. And let's go to the third term. Here we have a third term, and of course here we have force. And force assumed in this course is just given by minus q times E electric field in the case of electrons. Of course, if we are talking about whole gases, then the force will be given by positive Q multiplied by electric field. But forget about holes. Yes, also this electric field is only dependent on real space. It does not depend on momentum space. So that means that this first term can be safely once again pulled out from this momentum space integral. We can have the first term outside of our integration, and the remaining thing is now integration of our gradient of f. However, that is the gradient inside the momentum space, and just to take once again the integration. So it means that, simply speaking, we first take derivatives and just to integrate. Then what will happen? As a result of this integration, you will have the values at zone boundaries. However, we assume that now we have, if we go to zone boundary, then there will be negligible electron distribution function. So we assume that now this red colored integral becomes 0. Now we have in the integrated Boltzmann transport equation, this force related terms goes away. Then now we have only two surviving terms, and let's just summarize them. So now we have only two terms, and two term here we can easily identify the quantity of integration of velocity times distribution function. So if we just integrate the f over momentum space, that will be related with electron density. However, what we have to do now is not just integration of distribution itself, but we have to calculate the integration of v times f. So then what is it? Can we find any information about this quantity? So right now we have no idea. So our strategy is, okay, we cannot find any information about this integral. So just to define it as electron flux. So physically it is quite sound because so here we have occupancy of a certain state and its group velocity. So it means that if f equal to 1, fully occupied, and if velocity is this one, then this electron just contribute to certain flux. And if we have 0.5 half-filled state and its group velocity is given by this way, and it just contribute to the flux of half multiplied by this group velocity vector, and their sum will give us a certain quantity corresponding to the electron flux. So now we have electron flux defined exactly in this way, and with this definition of electron flux, now we can easily identify this part is actually corresponding to our electron flux. And of course here we have a divergence term, and when we just make it clear, then this one will be the equation. So simply speaking, time derivative of electron density is related with the divergence of electron flux. If electrons move away from that position, then electron density will be reduced. And on the other hand, if electrons are coming into this volume, then electron density will be increased. This simple rule is described by this continuity equation. You know that continuity equation is quite a general one, not only for electrons, but if we are talking about other physical quantities, you will find that there are so many, arbitrarily many, continuity equations hold. Yeah, and let me just introduce electron current density. Now, electron flux is just carrying the number. The electron current density describes the charge transport. So flux F sub n just to describe the number transport. However, now we have to multiply minus q. Each electron just carries minus q, so that can be a proper quantity to be considered in the microelectronics. So now this quantity is flux multiplied by unit charge carried by our electron is called as electron current density, and typically we just write down in this way, J sub n. Then how can we rewrite the electron continuity equation with electron current density? So as you can see here, electron flux is simply given by 1 over minus q Jn So now you can see that round n over round t minus q 1 over q and real space gradient and Jn now becomes 0. That will be the continuity equation written in terms of electron current density. Maybe you will find that this form is more frequently used in literature. Anyway, this is the continuity equation, and now let's go to the second equation. The second equation is just extension of our first trial to more complicated cases. Instead of just integrating the Boltzmann equation over momentum space, we multiply velocity first, and this is the Boltzmann transport equation multiplied by this velocity. As you can see that here you have velocity, and here you have velocity, and here you have velocity, and here you have velocity. Nothing special. But maybe you can ask me why we have to multiply velocity instead of for example energy or mass or well any kinds of physical information can be multiplied to the Boltzmann transport equation. And in principle you are right, you can do anything. You can multiply any quantity to your Boltzmann transport equation and take the integration over the momentum space. That is just a recipe. However, the main motivation for us to multiply the velocity instead of other quantities is when we talk about the motion of electrons, or when we count the change of electron density, then obviously we have to understand Jn or f sub n, and this is nothing but just given by integration of velocity times f. Vf term is of our interest, so that's the reason why we multiply this v to Boltzmann equation, and after that just to take the integration. Then I have summarized it here, and as you can see this time derivative can be easily pulled out because time derivative is nothing related with this integration. And here you can see, yes, this is v times f integrated over momentum space. You can easily understand this quantity is related with our electron flux. Oh, now this integrated Boltzmann equation now describe the time derivative of electron flux. Previously, our integrated Boltzmann equation described time derivative of electron density. Why? Because at the time, we have not multiplied any physical quantity to the original Boltzmann equation. But now, our Boltzmann equation is multiplied by the velocity, so the integrated equation now describes the motion or time evolution of electron flux quantity. And if we multiply any different physical quantities, and you will find that this time derivative term will describe any quantity corresponding to that multiplied quantity. Okay, so this is the way to generate many equations. However, since our interest is laid on the current density or electron flux, so that's the reason why we just multiply V here and easily understand this is corresponding to flux itself. And now we have 3 more terms. So the first term, second term, now we have second term, third term, and fourth term. Oh, in this case, since we have additional quantity in the integrand, so it is not as simple as in the previous case. We have to spend more effort to calculate them. So let's go to once again term by term way. So if we remember the definition of electron flux, we can easily understand the first term is just given by time derivative of electron flux. Okay, it's okay. And well, all other terms are just written, copy and paste it, and no change here. And now first consider the third term. Third term is related with force, and let's do it. In this case, how can you calculate this term? Previously, if we don't have this v, then what we have done was just to pull out this first term out of the integration. Is it possible still? Yes, because force is still independent to the momentum space, so we can easily pull out the force. Okay, so let's go step by step way. So one thing we have to keep in mind is that now we have multiplied the velocity. Velocity is a vector, so we have to think about the component wise. When we consider the third term, now it has v, so eventually this integrated quantity will be again another vector. So, and its x-directional component is determined by actually vx, and here this is just a scalar, and its y-directional component is also determined by our v sub y, and this is a scalar. So I wanted to suggest that when we fix the direction, for example, x direction, y direction, and z direction, life can be simplified. So let's consider just a certain direction, x sub I, and this x sub I can be either x, y, z. So here we have v sub I. Okay, so it can be v sub x, v sub y, or v sub z, depending on your choice for I. And here you can see this term. This term isn't not changed any longer. And in this case, of course, we can pull out our force, because our force is nothing related with this integration. But point is, now here we have gradient of f, and previously this gradient of k and its integration was gone, because that gives you just boundary values of your distribution function, so that they are gone. However, in this case, it is not as simple as before, because we have to evaluate this quantity instead of just this quantity. We have to consider vi. So this is not total derivative. So what we have to do is just to make it a full derivative and take the minus and vi's gradient and f. That is just integration by parts, and by applying the same argument, we can easily assert that this term goes away. Okay, because when you go to the boundary of our momentum space, then this f will vanish eventually. So now they are gone. And however, this term does not vanish. So yeah, that is true. So that's the reason why here we have minus integration term, and here we have minus integration of what? F times gradient of V, and F times of gradient V across here. So it is nothing but we have applied the integration by parts. Okay. Then we need more effort to understand this term further. Okay. So now here we have the term like this one. This is, for example, x directional velocity or y directional velocity or z directional velocity. And now we have to calculate the gradient of this quantity. So now we have this quantity, gradient of certain velocity component. Then although this vi is a scalar value, however, this one taking the gradient will give you what? Will give you another vector. So this vector will have also component, and also it is depending on the direction of our velocity v sub I, vx, vy, vz, that will change the result. So let me just write down. I mean that this and this term will give you, for example, f x direction, fy y direction, and fz and z direction. That will be the result of this electric force. And here we will have something like this. Here round vi over round kx and x direction, and y direction vi over vky, and eventually here we have vi over kz. So if we evaluate this dot product, then you can easily find that that will be fx multiplied by round vi over round kx, and fy round vi ky, and fg vi kz. So here indexes are just repeated x, y, z, z. So in this notation, I just introduce j, and this j can be either x, y, z, and here we have fx, fy, fz, and also here you can see that this quantity. So this quantity round vi over round kj, that is now written as, together with this 1 over half bar, this one is just represented as inverse mass. So let me just more clearly write down its definition. So simply speaking, m inverse mass and its component ij is simply given by 1 over half r and round vi and round kj. Okay, so you can easily understand this one. Okay. So, well, for sometimes this inverse mass can be quite difficult, and for some materials this can be quite simple. But when we derive this drift diffusion model, we will just introduce isotropic material, and we will assume that this inverse mass, which can be in general dependent on I and j, can be just represented as diagonal tensor. So the simplification now introduced here. Effective mass approximation is introduced here, and inverse mass, it can be actually non-zero values for any index pair ij. However, we will say that inverse mass xx is just 1 over m star, and myy is just 1 over m star, and mzz, that will be also another terms 1 over m star. They are all the same. And how about other non-diagonal terms? For example, mxy, mxg, or myz. Those terms vanish from our assumption. I mean that, is there any counterexample for this vanishing of diagonal terms, non-diagonal terms? Yes, we have plenty of them. Actually, many electronic structures does not satisfy this simple approximation. Our mass, inverse mass, cannot be represented as just a diagonal one. However, in this simplification, we will introduce this crude approximation. Yeah, so you don't like it, and yeah. However, that is a usual trick we should follow. So if we follow just diagonal approximation about diagonal and isotropic, then we can make a great simplification. Oh, here we have actually summation of j, but now from the assumption of isotropic band structure, isotropic and diagonal band structure, we can understand, although we have here summation over j, but only term which does not vanish is when j equal to I. So now we say instead of j, we can say fi and 1 over cube of 2 pi and integration of momentum space, and this inverse mass now just becomes 1 over m star and f. Ooh, then what happens? Now this 1 over m star can be regarded as just constant, so why don't you just put it out? Then you will find that now this remaining integration of f over the momentum space will give you just electron density n. So now this one is the component for your xi direction. For example, if we are talking about x direction, and x direction component now becomes minus fx 1 over m star n, and y directional component now becomes minus fy 1 over m star n. Also finally we have z direction and fz and 1 over m star n. So by combining them, So those quantities can be regarded as just scalar quantity, and you know that this one will give you just a first term. So now I wanted to conclude this short discussion about third term. If we are talking about third term, if we introduce a certain approximation for our band structure, so effective mass, then now we can say this third term is greatly simplified by minus electric force 1 over m star and n. So that is the second term. That was the third term, and let's go to the second term, and now we can follow quite a similar approach. So first let's go to the second term, and how does it look like? Okay, it has also certain terms, but by taking our previous trick, also we will say here we have only I directional component. Now this one can be written as v sub I under the fixed direction, xi direction, and here we have still quantities. In this case we have to have vx and round f over round x plus vy round f over round y plus vg round f over round g. So that can be expressed as vi times introduce another summation j and vj over round f over round xj. That will be enough for this calculation. So let's go to the second term here. Then now we introduce j summation and have this term. This term is corresponding to our previous parenthesis. And now you can see that this once again this real space derivation is nothing related with this momentum space integration, so we can pull out here. So then now this is the form for second term. Then let me just collect them all. Then you can see that this is the first term related with the time derivative, and this one is related with the velocity, and this term is related with the electric force, and this is related with scattering. Oh, so among four terms, you know, this is easily accessible. And fortunately also this term is quite accessible. This is I directional, xi directional component of electric force, and this is a constant inverse mass, and here electron density. All of them are quite accessible to us. So our remaining task is, although they are simplified, still we have to think about this second term and first term. They should be further simplified. So in order to do that, we have to introduce more approximations. So now our first target is the last term, the scattering terms. So scattering term is, please make a comparison between these top equations and bottom equations, and you can see that the first term is just kept as before, and third term it's okay, and we just keep the second term, and we have made a simplification for these scattering terms. So what happens to our scattering terms? How can we change it to fn, I? Please don't become confused with this fi and fn, I. This is related with electric force, and this is related with our electron flux. Their xi directional components are written here, so don't be confused. They are completely different quantities. So anyway, how can we approximate our scattering related terms in this way? So in this case, we have introduced certain approximation. Our scattering integral can be approximated as minus f minus equilibrium f divided by relaxation time tau. So if we introduce this approximation, if our S can be represented by this way, then why don't we just insert it and evaluate it? Then you will find that if we insert this term, 1 over cube over 2 pi and Brillouin-John integration and V I F and plus minus Vi equilibrium F divided by 1 over tau and dk. Of course, we should have minus here. That will be the result of just insertion. And you can understand the F of EQ is nothing but the equilibrium distribution function, and this is integration of velocity times distribution function that is corresponding to the flux. However, if we use the equilibrium distribution function, then the related flux is just 0. When we evaluate this term, when we evaluate the integration of this term, that will give you just number 0. So we don't care about this term. However, this one, the first one, related with the real distribution function f, that gives you the flux term. So shortly speaking, this one, and this one, this one, and this one will give you the xi directional component of your electron flux. So that is even here. And here you have an additional minus factor and 1 over tau. So now with this approximation that is called relaxation time approximation, here we have a relaxation time. By adopting this relaxation time, then we can easily make our scattering into quite a simplified form. So what is the significance of this approximation? By taking this approximation, the complicated scattering can be just expressed as a term related with f sub n and tau. Okay, this tau, the relaxation time, can be modeled. I mean that we can introduce certain reasonable numbers into it, and also this Fn, electron flux, is our interested quantity. Previously, our scattering terms was really difficult to deal with. However, now this simplified form is easily accessible to us. So then, now our remaining task is the second term, and of course, we will try to express this second term in terms of, for example, electron density or flux. That will be our goal, and introduce certain quantities which can be easily modeled by additional effort. That will be our strategy for remaining second terms. Then second term, in order to calculate the second term, we have to consider this one, multiplication of Vi and Vj and multiplying also f, and their integral should be calculated. Oh, how can you do that? In this equation, we just multiply tau to everywhere. So you can find here tau, and here tau, and here tau. But this is just a multiplication. And the remaining thing is now we have to consider integration of this quantity. Oh, this is tau vi vj f. How can you do that? So what we do is just collecting them all, and just treat it as electron density, because here we have F and additional quantity. So this average quantity corresponding to this one average quantity of this tau velocity, this quantity is just defined as, once again, electron diffusion constant, electron diffusion coefficient d sub n. That is the trick. You know that this is really difficult to evaluate, but we just say that, okay, we have no idea about this quantity, and we will call it as a new quantity called diffusion coefficient. So that's it. Then, of course, all kinds of important information is still hidden in d sub n, and we will try to find out a good way to model d sub n. That is usual trick we do. So now, if we adopt this form, then, so simply speaking, we'll say this integration now given as q times gradient of dn n. Yeah, so that is written here. That is the simplified form of our integrated Boltzmann equation. Of course, that Boltzmann equation was multiplied by the velocity vector. And now, when we consider the steady state solution, here steady state means that this time derivative, all terms related with the time derivatives goes to 0. So we have no terms related with the time derivative. Then you can see that this is nothing but just j sub n. Now our j sub n can be expressed as here we have force related term. So let me just write down once again, minus f and q tau over m star is written as mobility and n. And you know that we have introduced this form for electric force. When we insert it here, then we can find q times mu n n e. So this is corresponding to the so-called drift term of our current density. And this second term, yes, this second term also can have two quantities. For example, q times dn gradient of n plus q times n gradient of dn. However, also we neglect this second term because spatial variation of d sub n is neglected. Then now we have so-called diffusion term. Okay, so Are you with me? So eventually, let me just summarize our whole long lecture. So from the integrated Boltzmann equation, we have introduced severe approximations. What was it? For example, we assume that the band structure is position independent. Okay, that was it. Also, we have introduced effective mass approximation. Okay, we introduce it. Also, we have introduced also relaxation time approximation. Okay, that is also severe approximation. And we have also modeled our complicated quantity, this integral, as just a product between diffusion coefficient and electron density. And we have assumed once again this diffusion coefficient, which can be in general a tensor quantity. However, that is regarded as a scalar quantity. Maybe you can feel that, okay, this derivation procedure introduces so many approximations, and whenever we introduce approximations, then physical accuracy of this derivation is degraded, and you are right. So the final expression, which is frequently called as a drift diffusion equation or current density expression, is not as accurate as a Boltzmann transport equation. It includes a lot of approximations, and in order to make it accurate, we have to spend quite a long time about this modeling of this mobility and diffusion constant. However, anyway, this one is just a function of real space. No information is required for momentum space. So although we have sacrificed many beautiful things, physical rigor and accuracy, however, instead of that, we have got efficiency only depending on the real space. Okay, so this is the end of our discussion about deriving two equations in the drift diffusion scheme. So in the next lecture, we will try to implement it and solve it by our numerical means. And thank you and see you.